Welcome to video 4.2, constructing arithmetic sequences.
Today we're going to explore arithmetic sequences, and we are going to talk about how to create them and what they are. So first and foremost, we're going to start out with an example. So in our example, you can order tickets for the local theater online. Okay, and there's a fee of $2 per order. The matinee tickets cost $10 each. So again, that important information is that you have $10 each, and that it's $2 per order. All right? The total cost in dollars of ordering N matinee tickets, so N is your number of tickets, can be found by using C of N is equal to 10 times N plus 2. The table shows the cost of 1, 2, 3, and 4 tickets. So here we know that if we plug in our numbers, so again, usually it's that whatever we plug in for N is our position. In this case, the position in the sequence is the number of tickets we're purchasing. So if we plug in 1, we know that it's going to be 10 times 1 is 10, and that's going to be $12. And if it's 2, that's going to be $22. And 3 is going to cost us $32. And 4 will cost us $42. All right, so then in this case, the domain of our sequence is 1, 2, 3, and 4. Those are the only number of tickets that we purchased. And then the range of our sequence is 12, 22, 32, and 42. And then what is the first term of the sequence? The first term of this sequence would be 12. Right, so that all should be review at this point. And then now we're going to look at the patterns that we're finding here. So we notice that 22 minus 12, so our second term minus our first term gives us 10. Our third term minus our second term gives us 10. And our fourth term minus our third term gives us 10. All right, and this is going to help us when we're talking about what an arithmetic sequence is. So I want you to keep this in mind that we have that consistent difference of 10. Right, so suppose you extended the table for up to 15 tickets. Would you expect the difference between consecutive terms to be the same? Explain your reasoning. Right, so in this case, would you expect it to be the same? Well, since you only have that $2 fee that one time, every time you know that your price is going up by 10 because every ticket costs you $10 more. So yes, I would expect it to go up by 10 every single time because of the fact that every ticket costs $10. Okay. Because the cost per ticket is $10. All right, so then the second part says, explain how the domain is limited in this situation. Well, what it's asking is, can your domain be different numbers? And in those different numbers, are there options that you can't use? So when looking at this, our domain was 1, 2, 3, and 4. Now here's the thing, we're talking about number of tickets purchased. So thinking logically, can you purchase 0 tickets? No, because if you're not purchasing any tickets, you're not going. Right? And can you purchase negative tickets? No. So in this case, your domain is limited to non-zero numbers. So your domain is limited to whole numbers. Okay? Especially since you can't buy half of a ticket or 3/4 of a ticket. So the domain is limited to whole numbers. All right, so here we go. Moving right along again with a little bit more of an explanation here. So you need to understand that an arithmetic sequence is when the difference between consecutive terms is always equal, right? So when we go back to that first example, we said the difference was always 10, 10, and 10. So that would be considered an arithmetic sequence. Okay, this difference written as D is called the common difference. Okay, so the common difference is the difference between the numbers or the terms in a numerical sequence or in an arithmetic sequence. All right, so in example 1, you have the table that shows the monthly balance in a savings account with regular monthly deposits. So since it's regular monthly deposits, that means that you're always getting a deposit of the same amount. All right, so in here, we're writing a recursive rule. Remember, recursive means that the next term in a sequence depends on the previous term. And we have to look at the table and what it's telling us. So in the first month, they have $2,000. So we know that f of 1 then is $2,000 because that's what they start with in their bank account. And in this case, every month it goes up by $500. Since that's consistent, we can call that the common difference. So D is equal to 500. So the recursive rule in this case is that you're always taking your previous amount and you're adding 500. So if we look at the first month, we added 500 and got 2,500. Then we had to add 2,500 to the second one to get 3,000. Okay, so our rule is that f of n minus 1 plus 500 is equal to f of n. Okay, and it has to be for n greater than or equal to 2 months. So this is where that fact that we have to know what this is, we have to know that f of 1 in order to be able to work through our recursive rules. Right? Since D is always multiplied by a number equal to n minus 1, you can generalize the result from the table. So you're easily able to say that it goes up by 500 each month, so it is an arithmetic sequence. And you're easily able to say that you know that you're taking the previous term and you're adding 500. Okay, but now if we wanted to write it as an explicit rule, we would have to look at the fact that, so since D is always multiplied by a number equal to n minus 1, you can generalize the result from the table. So that means that the explicit rule is f of n equals 200 plus 500 times n minus 1. So what that means is you can say that my initial balance was 2,000 and I'm always adding 500. However, if I'm always adding it to the 2,000, then the amount that I'm adding each time goes up. So for the first one, so for n minus 1, so what that means is, like for position number 2, if I take 2,000 and add 500 times 2 minus 1, that means that I'm taking 2,000 and I'm adding 500 times 1, which is 2,000 plus 500, which is 2,500. Okay? We are going to talk more about how to create these functions, but what I need you to understand is that for some, you can always create recursive or explicit rules. All right, so here we go. So we're going to try one a little bit more on our own. So in the table, we have the monthly balance, and it also gets regular deposits. So we know that that word regular is incredibly important because that's telling us that it's consistent. That should tell you that it's an arithmetic sequence because the difference is going to always be the same. So to write the recursive rule, we have to first know f of 1. So in the first position, we have 5,000. So f of 1 is equal to 5,000. Okay, and the common difference, so going between each number, we're adding 1,000 each time. So the common difference is 1,000. So then the recursive rule in this case is that f of 1 is equal to 5,000, and that f of n is equal to f of n minus 1 plus, oops, that should be a 1, 1,000. Okay, so it's telling you that if you take the position, so if I take the first position and add 1,000, it should give me the second position, and so on and so forth. Okay, now, if I want to write it as an explicit rule, I have to look at my position and what I get, and what that's going to look like within my function. So in the second spot, I have $6,000, and in the third spot, I have $7,000. Okay, so I'm always starting with the 5,000, so it's always going to be my f of 1 plus, well, what is my common difference? My d in this case is 1,000, so I'm always adding 1,000 times my n, so times my position. Oops, not n, sorry. Times my f of n minus 1 times f of n. Oh my goodness, I can't talk today. Times my n minus 1. All right, so since d is always multiplied by a number equal to n minus 1, you can generalize the result from the table and say that 5,000 plus 1,000 times n minus 1 is your function. So let me go back to the table here and give you a better, so I'm going to give you a better example in the table as to why this piece of it works. So we know that to get this 6,000, I have to do 5,000 plus 1,000, and it has to be 1,000, so whatever I multiply, so in order to get 6,000, it has to be 5,000 plus 1,000. So I need to know, what do I multiply 1,000 by to keep it as 1,000, and I know that that is 1. Here, I need to end up adding 2,000 to my 5,000, so, but I can only add 1,000 times something. So to turn the 1,000 into 2,000, I multiply by 2. Now, if you look here, you have your n is 3, and what you're multiplying by is 2. Your n is 2, and what you're multiplying by is 1. So you're always multiplying by your n minus 1. All right, Jerome says that the sequence 1, 8, 27, 64, 125 is not an arithmetic sequence. Is he correct? Why or why not? So I want you to take a second to think about this and then come back and check your answer. Right, so Jerome is saying that it's not an arithmetic sequence. Is that correct? And in this case, it is correct. Okay, and it's correct because the difference between the consecutive terms is not always the same. Okay, so there might be some sort of rule sometimes that works. However, the difference has to be the same. So in this case, the difference between 8 and 1 is 7, and the difference between 8 and 27 is 19. So right off the bat, you know that those two differences aren't the same, so it cannot be an arithmetic sequence. There we go. So yes, Jerome is correct because the difference is not always the same. Okay, and if an arithmetic sequence has a common difference of 3, if you know that the third term of the sequence is 15, how can you find the fourth term? All right, so here we know that the third one is 15, and I want the fourth one. Well, if the difference is always 3, then I know that I can add 3 to the third term to get the fourth term. So now we're going to take a look at how to use a general form to construct rules for these sequences. All right, so you have a recursive rule and you have a general explicit rule, and we're going to look at how to put those together using a formula, so to speak. So for A, so we're going to write a recursive and a general recursive and a general explicit rule for each. So we have 100, 88, 76, and 64. So the easiest part is always to find that f of 1. That f of 1 is always your first term. In this case, your f of 1 is 100. To find the common difference, you're just going to subtract. 100 minus 88 is 12. 88 minus 76 is 12. 76 minus 64 is 12. So you know that that common difference is 12. right? So then for your recursive rule, in general, it's going to be f of n is equal to f of n minus 1 plus d. And it has to be, n has to be greater than or equal to 2. So that's telling you that your domain numbers have to be 2 or larger. So then in this case, I would plug in for d, and I did. Then when I plugged in for d, I plugged in 12. So I know that my general rule is that f of n minus 12 is equal to f of n. Right? So here is my general rule, and I'm just plugging in for d. Okay, but since I'm going down by 12 each time, it changed from, so I know that it says f of n minus 1 plus d. Okay, so f of n is equal to f of n minus 1. None of this is going to change. Since we're subtracting 12, so I'm going down in this. I'm not going up, I'm going down. So since I'm going down, it's subtraction, and the common difference is 12. Then now with my general rule, so my general rule for explicit is that I always take my f of 1 plus my d times n minus 1. So if you notice that pattern previously, it's because it's an actual rule. It's how we can easily put together a function based on our common difference. So in this case, I have my f of n equals, well, 100 was my first term, minus 12, which was my common difference, times n minus 1. Again, you know it's not recursive because you have no function inside of this part of your equation. All right, so some guided practice here. If you want to try this on your own, go ahead and pause and then come back and check your work. Otherwise, here we go. So f of 1 in this case is 0, and the first position is 0. And then I know that my common difference, so I can look at 8 minus 0, and I get 8. And that's the case all throughout my sequence. And I'm going up, so I know that my addition is going to stay. So the addition from this rule up here will stay. So because it's f of n is equal to f of n minus 1 plus d, so in this case it's going to be plus my 8. And then I have to tell everybody that f of n is equal, or f of 1 is equal to 0. They have to know that my first term is 0, otherwise they can't find the other pieces. All right, then the explicit term, so right here I enter my f of 1, which is 0. And then right here I enter my d, which is 8, and I'll multiply that by n minus 1 each time. So if you use this rule, both of these rules, you can create your recursive and your explicit rules. You just have to know your constant difference and your f of 1. Okay, so what is the recursive rule for the sequence f of n equals 2 plus negative 3 times n minus 1, and how do you know? So this is since it doesn't have the f of n, you know that this is your explicit rule. And we want to figure out what is our recursive rule. Well, we know the recursive rule is always f of n equals f of n minus 1, plus my common difference. Okay, so in this case, and I know that for my explicit, it's f of n is equal to f of 1 plus my common difference times n minus 1. So here, because of this, I know that 2 has to be my f of 1, and that minus 3 has to be my common difference. So now I take these numbers, so I take 2 and I take negative 3, and I plug them into my recursive. So the equation would be f of 1 is equal to 2, and then the function is, I'm sorry, f of 1 would be equal to 2, then the function is f of n is equal to f of n minus 1, and you could do this one of two ways. You can say plus a negative 3, or you can say f of n minus 1 minus 3. Whatever way you're comfortable with is fine. Okay, so I'm substituting what I know from the explicit into my recursive. Because again, you're always using f of 1 and the common difference. Okay, so now we're going to write a rule for the recursive rule and an explicit. I want you to pause and come back and check your answer. So we have to find the common difference. The common difference in this case is 10, and we're going up 10, so it's a plus 10. And our f of 1 is 6. So for our recursive, we know that we first have to tell that f of 1 is equal to 6. And then our function is f of n is equal to f of n minus 1 plus 10. And then we do have to add to that for n being greater than or equal to 2. For my explicit, I do not have to tell what f of 1 is because it doesn't matter because it's an explicit rule. However, I know that f of n will be equal to my f of 1, which was 10, times, well, I'm sorry, not my f of 1 being 10. F of 1 isn't 10. My f of 1 was 6. 6 plus my change, my constant change, or my constant difference, times my n minus 1. Jump the gun there, I almost forgot my f of 1. Okay, again, I don't expect you to come in to the next class and have all this memorized, but I do expect you to be able to identify your f of 1 and your common difference and to be able to plug them into these two general rules so you can create your own rules. All right, and then now we're going to relate the arithmetic sequence to functions. So you know that functions are, or an equation is a function if every input has only one output. That's incredibly important to understand that any input, so if I put in 1, I can't get anything other than 75. If I do, it's no longer a function. So when it comes to sequences, if it's an arithmetic sequence, since the change is always the same, it would have to be a function. Because if I put in 1, I should still get 75, but then when I put in 2, it should go up by however many the common difference is. And in this case, we can see that it's 25. So it would have to be a function. All right, so when you're doing this, so you have your graph, and it shows you the sequence. So the sequence is in position 1, it's $75. Position 2, it's 100. Position 3, it's 125. And position 4, it's 150. So for one passenger, it's 75. 2 passengers, 3 passengers, 4 passengers. Okay, so then what we're going to do is we're going to take it and we can represent it in a table. And then we can find the common difference. Again, we found that the common difference was 25. And once we realize that it was 25, okay, because if you go through and check all of them, we know that it's 25. Once we know that it's 25, we can write an explicit rule. So I know that my explicit rule has to be f of n equals my f of 1 plus my common difference times n minus 1. So here my f of 1 is 75. So f of n is equal to 75 plus my common difference for this is 25 times n minus 1. Sorry, that's supposed to be a parenthesis. Okay, and then I know that that has to be for n being greater than or equal to 2. Because I can't have negative passengers. All right, so let's try this again. So here, when I have one row number, I have 6 seats. Or one row, I have 6 seats. In 2 rows, I have 9 seats. In 3 rows, I have 12. And in 4, I have 15. So here I find my common difference, and I do 9 minus 6 is 3. 12 minus 9 is 3. 15 minus 12 is 3. So then I know the common difference is 3. So then I substitute 6 for f of 1, and I substitute 3 for d. So here I have f of n is equal to 6 plus 3 times n minus 1. Okay. So in this case, we are going to just skip the reflection question. I don't feel that it's necessary. I want you to go ahead and do the your turns, which are numbers 5 and 9. And then I also want you to do the elaborate questions, 10, 11, and 12. Again, I don't expect that you are a master at this, but I do expect that when you come into class, that you are able to identify the f of 1, the common difference, and given the rule, you can plug them in to create your recursive and explicit rules. As always, if you have any questions, please be sure to email me or write them down so we can go over them in class.